Please start.
Okay, thank you. So I remind you, this is a figure I showed yesterday. This is n sub k, the mode density as a function of wave number k. And k tilde is k over AE and this is n sub k over AE cubed HE cubed. AE is the scale factor at the end of inflation, and HE is the expansion rate at the end of inflation. So if K over AE is equal to 1, that means that the mode is just coming into the Hubble radius at the end of inflation. So at the end of inflation, those modes are outside of the Hubble radius. K is smaller than the value at the end of inflation. And out here, they are sub-Hubble radius. And this is the numerical calculation of the mode equations, and then translating that into n sub k. This is for a conformally coupled scalar for 3 values of m over he. And numerically, we see that for low k, it increases as k squared reaches some maximum and then decreases as k cubed times some exponential in k, and then eventually goes as k to the minus 3 halves. And this behavior is understood, can be modeled as annihilation of 2 inflaton fields during matter domination into the dark matter field. All right, and
only in a very narrow range of cases of inflection -1 to 0 is massive info. Outside.
Well, this will continue down for arbitrarily low k, and this will go as k to the minus 3 halves for very large k. Now, chalk. What we want to calculate is the co-moving number density. N is the co-moving number density, and this is the integral dk over k times n sub k. So we would integrate over all wave number. So this is, d log k. So if you want to know what the value of this integral is going to be, a good approximation, since this is a peaked function, is to just take the value here, and you see it's around 10 to the minus 5. To get a better answer, you would do the integral, and I'll do that in a moment. But this is what we want to do. But the spectral density is the power per logarithmic interval in k. For the scalar? For the spectator field? Yeah. Well, this is taken into account in the Bogolubov calculation. So, there are fluctuations in the field, and where the fluctuations in the field are, it's displaced from the minimum. That is correct. And this is it's called a gauge-dependent answer. So if you want to look at fluctuations in the field, then you look at a particular time. And how you do the foliation of space-time to look at a particular time is a gauge transformation. And in the, there are different gauges that you can choose, so that the answer to your question is gauge dependent. Okay?
In this slide, the energy density coming from the misalignment should be equal because it should have a different energy spectrum from what you calculated. So
this accounts for the misalignment energy density. So the misalignment energy density is you have certain fluctuations in the field during inflation, let's say. You know, the typical fluctuations in the field is h over 2 pi, right?
right.
And, but that averages to 0. You know, the mean is 0.
Right. But what people, as far as I know, what people talk about is that they talked about the dispersion instead of just the mean value. Mean value vanishes, but dispersion does not. So it, in average, it just still contributes to the energy density from such a fluctuating misalignment, different from axion. That's why. Yeah.
So this will show up in calculations of isocurvature perturbations, and that's the sort of the 2-point function. So now I'm calculating the 1-point function.
Okay.
So the fluctuations show up as isocurvature fluctuations, and that is the 2-point function.
Okay.
Now, here, if and there'll be a big difference whether the spectrum is blue for small k or if it's red. Here, the spectrum is blue. You know, for small k, it decreases as k squared.
I see.
So let's talk about it maybe during the break.
Okay.
Thank you. Okay. Okay. So remember what we did to get some analytic understanding of the spectrum? We started in, can you see this in the back? Or do I have to put the screen down again? It's okay. So we started here in, at the end of inflation and looking at the solution to the mode equation in de Sitter space. We approximated what it would look like at the end of inflation, and then followed the mode as it evolves in A. And in doing this, we found that the final result and this is for m over he smaller than 1. The result was and this happened for m tilde to the 1/3 larger than k, larger than 0. And then you can do the calculation that takes into account the high frequency damping. And then there could be an additional contribution from 2 to 2 scattering, where this is proportional to k squared, to k to the minus 3/2. Now I'll put a asterisk here, because if we're doing 2-to-2 scattering, so if we're considering phi to chi, we have to have the mass of the chi, I'm sorry, the mass of the phi, the mass of the inflaton larger than the mass of the chi. And for a quadratic potential, the mass of the inflaton is 2 times He. So this would only happen for masses smaller than approximately He. Furthermore, there's a minimum value of K we have 2 phi's at rest that are annihilating to 2 chi's. The phi's at rest, the momentum of the chi is going to be K over A. And so K is equal to M phi times A. The smallest value of A would be A at the end of inflation. So this 2-to-2 scattering, the Boltzmann approach, is not as general as the Bogolubov calculation. Okay. Now we can calculate A cubed n sub k just as the integral and let's just, it's going to be exponentially damped for larger k. So let's just consider this Excuse me?
This 2He greater than M chi, why is 2? The above equation.
For this?
Yes.
So for quadratic inflation, M phi, and I forget whether it's a 2 or a 1/2. Here I say it's 2.
Yes.
Okay?
Okay.
Now for hilltop inflation, so there can be a real sort of hierarchy between M phi and He.
I see. Okay.
So the end of inflation is calculated by A double dot equal to 0, and that involves the potential.
Yeah. Thanks.
Did that answer your question? Okay. So integrating this, let's just pick the low end. This turns out to be M tilde. So this n sub k goes as k squared divided by k is k. Integral dk times k is k squared. Evaluated at m to the 1/3 is m to the 2/3, and n sub k has a factor of m tilde to the 1/3. So this just ends up being proportional to m tilde. Now, of course, there are values of 8 pi squared and things like that in it, but this is what it's proportional to. So for small values of m over he or m over m inflaton, a cubed times m, a cubed times n is going to be linear in m. So this is the result for Na cubed. So this is the calculation of the co-moving number density as a function of the mass for conformally coupled scalars. And this is the result of the numerical calculation, but we can understand this from these analytic approximations that we have had. Now, what do we do with this? Let's do something interesting. Let's calculate omega h squared. So could this be, if it is stable, could it be a dark matter candidate? So Na cubed, a cubed times n, is constant so it's constant at late time. So the mass density contributed by chi today, and I'll say the 0 for today, is the mass times the number density today. So write it as n0. And this is the mass times n0, a0 cubed, over a0 cubed. This is constant in time. That's what we just calculated. So this would be the mass energy density in chi today. And we're going to compare this to the critical density today. The expansion rate today is the critical density, is the density over 3 m Planck squared. So the usual thing to define is omega, the contribution to the critical density carried by chi, mass times Na cubed good. And this we've just calculated from gravitational particle production. Now, what is A0 cubed? assuming that the entropy, the total entropy, remains constant, A0 after the reheat temperature, so the total entropy, the entropy density is proportional to T cubed. The total entropy is A cubed times S, and this is a constant as long as the number of degrees of freedom, et cetera, remain constant. Yes, from the time of reheating, when we have a radiation-dominated universe, until today. So this is why we started a radiation-dominated universe. The decay of the inflaton field increases the entropy. So after inflation, the universe is in a low entropy state. And then as the inflaton field decays, the entropy increases. And then when the inflaton field goes away, you're in a radiation-dominated phase, and this would be the behavior of A0 and T0 in the radiation-dominated phase.
Here we are considering production to pi pi to pi pi. You said inflaton decay will affect the entropy.
So it will, first question is that what is the decay, decay products? What are the decay products? And secondly, there could be a production of chi-like particle from the decay itself, right?
Not necessarily, because then you would have to have a coupling, a direct coupling of the inflaton field.
Right. With the graph, yeah, I got it. Yeah, second one I got it. So even for the decay, you need some portal coupling, right? Some interaction.
For the decay, you need for the decay of phi, for
Yes.
reheating, you have to have a coupling between the inflaton field and standard model particles.
This is what I'm assuming.
So we're assuming the inflaton field decays into standard model particles. Standard model particles. And once the inflaton field decays, these two-body processes, phi-phi to chi-chi, go away.
Yes, because they are more strong.
Because it's not there in the vacuum anymore.
Okay, so there would be an epoch where this thing will die down, right? So this production will stop.
Right. And this also introduces, so remember for large K, when we calculated n sub K, it goes as K to the minus 3/2. This doesn't continue forever. So the production of the chi is a resonance process where phi-phi goes to chi-chi. These are at rest. So the momentum of the chi is equal to m phi. So the physical momentum is K over A is equal to m phi. So K, you produce the particles when K is equal to m phi times A. So A is increasing. As the universe expands and A is increasing, you're having resonant production of higher and higher values of K. This stops at when it reheats. So K max so there'll be a cutoff in K, so it will continue as K to the minus 3/2 and then stop at that value of K.
Okay, and then it will be constant in the...
And it goes to 0. Then you no longer produce the particles.
Right. And if I don't consider the decay of chi, then the relic of the chi would be
The,
kind
the
of,
decay of phi, the decay of the inflaton field.
yeah, but let's say chi has produced with the K max, and after that there's no production, right?
Right.
So if chi doesn't decay after that, then the relic of the chi would be kind of constant.
The what, sorry?
Relic of the chi today.
Then if there's no production after that, I'm assuming that the chi is stable.
Yes, so kind of dark matter.
Right.
Yeah. And then the whole scenario is mimicking kind of a freezing kind of a phenomena, right? Because initial number density of chi was 0 before it start producing by gravitational interaction. Then at some point, it's like during reheating, it reaches whatever value. And then if it doesn't decay, like if it's candidate dark matter, then the relic could be a kind of a freezing relic.
Well, we don't know what the reheat temperature is.
Yes. Yeah. I mean, I understand.
Unfortunately.
Yeah. Thanks.
Thank you. Okay. What is a reheat? H at reheat is related to H at the end of inflation scaled by what it would be in a matter-dominated universe. So in a matter-dominated universe, H squared goes as 1 over A cubed. Then we're making the assumption that reheating is instantaneous. And H squared at reheat is going to be blah, 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 blah. 1 over the Planck mass squared times the reheat energy density, and this is T reheat to the 4th. And there are factors of 8 pi, number of the G stars and things like that that I'm ignoring. So I'm setting so small factors like 1024 pi cubed, I'm setting equal to 1. So I'm not worrying about any prefactors. So I can relate ARH cubed from this to AEHE and the reheat temperature. So A reheat cubed, I can get from this equation using H reheat in terms of T reheat. So putting this into the equation for omega chi, proportional to m chi. It's rho chi 0. This is rho critical is proportional to Na cubed. And 1 over A0 cubed gives a factor of T reheat HE over M Planck squared times T0 cubed. So let's see if we have the correct mass dimension. This is dimensionless 1, 2, 3, 6, 2, 4, 6. So at least I have the right mass dimension. And again, pi's and things like that I've set equal to 1. Now, if it is dark matter, the observed contribution of the dark matter density is omega chi approximately equal to 0.12. And if I put in the value of H0 today, T0 today, the Planck mass to the 4th power, and the reheat temperature, it's going to be linear in the reheat temperature. And it's going to be linear in HE. So I can write this as m chi over HE. So you can look up the present temperature of the universe, 10 to the minus 13 GeV or so, the Planck mass, 2 point whatever times 10 to the 18 GeV. It's linear in the reheat temperature, and it is linear in HE. So this suggests we'll call it the sweet spot.
Contribution because the decay of the inflaton would be model dependent. So,
Well, the decay of the inflaton is model dependent, but I'm picking it up once the universe becomes radiation dominated, which will happen when most of the energy density in the inflaton has decayed. So the thing that enters is the reheat temperature. So okay? Yes?
Inflaton decays to not only dark sector but also standard sector, then
So I'm not assuming that the inflaton decays to the dark sector. I'm assuming the inflaton decays to standard model particles to produce the primordial soup. Okay?
then why do you see 10 to the minus 5 specifically?
Why did I choose 10 to the minus, for fiducial values, 10 to the 9 GeV and 10 to the 12 GeV? Because 10 to the minus 5 is a good number. So it can change. We don't, H sub E is related to the inflaton mass. We don't know what the mass of the inflaton is. We don't know what the expansion rate of the universe at the end of inflation is. Most models have it in the range of 10 to the 12 GeV, have something large. There are models of inflation that have it very much smaller, and there are models of inflation that have it somewhat larger. There is an upper bound to the expansion rate from CMB observations, from lack of observation of the tensor mode of gravitational waves puts an upper bound on HE, but that's something like 10 to the 18 GeV. And it is, this relation that HE is related to inflaton mass over 2 is true in quadratic inflation. There might be a factor of 10 or 20 or so with other models of inflation. We don't know what it is. So this is something, this is what is calculated from gravitational particle production. So this does not depend upon the reheat temperature, and it only depends on the mass divided by HE. So this calculation is independent of the reheat temperature, but the contribution to omega today would depend upon the reheat temperature. So the universe, let's say at reheating, has a certain energy density in the chi and a radiation energy density. And the energy density in the chi is much smaller than the radiation energy density at reheating. But the energy density in the chi goes as a to the minus 3. The radiation energy density goes as a to the minus 4. So the earlier reheating, the larger this ratio would be. So the longer the universe goes through the matter-dominated phase, the larger omega h squared would be. If we have what, sir? Minimal coupling? That's the next thing I will cover. Thank you for the question. Okay, so this is something that's sort of interesting, that to get 10 to the minus 5 here requires a mass that's comparable to HE, comparable to the inflaton mass. Now, it could have been 10 to the minus 25, 10 to the plus 25, but it's something of order the inflaton mass. So the idea is that there is another scale in physics that's at a very high energy scale that drives inflation. So the inflaton mass in the inflaton sector is at some high energy scale. And the idea is that if once you have another energy scale in physics, you have many species of particles with mass comparable to that energy scale. So you could have a chi, having a chi mass comparable to the inflaton mass is a reasonable thing to come out. And it would become even simpler if m is smaller than HE, then A cubed times N is proportional to the mass, then and the 10 to the minus 3 comes as essentially 1 over 16 pi squared. So if this is proportional to the mass, if this is proportional to the mass over HE, then you see that HE is going to cancel in this. So this is proportional to linearly proportional to HE. And if NA cubed is proportional to HE, then the value of HE will disappear from this equation. And we are left with sort of a simple prediction . Where it only depends upon the mass and the reheat temperature. So if this ratio m over 10 to the 11, T reheat over 10 to the 9, if that's equal to 1, then it would be a good dark matter candidate. Now, we had the question about minimally coupled scalars, and minimally coupled scalars give a very different result.
What if that we consider the inflaton doesn't decay, only produces chi?
If the inflaton only produces chi, then I'm assuming the chi does not have any standard model any interaction, so you would not produce the radiation primordial soup that we see today. So everything in the universe that we see, forget about dark matter for a moment, the radiation, the matter, come from the decay products of the thermalized decay products of the inflaton. You are a descendant of the inflaton. Does that answer your questions? Yeah, all right. But it's the entropy, it's the radiation entropy that S counts. So this is the numerical result for A cubed N as a function of the mass, as a function of K for minimally coupled scalars shown here for C equal to 0 compared to the conformally coupled scalars. You see, it looks much different. In particular, for small mass, for m over HE smaller than 2, the spectrum is red. It has a logarithmic divergence in the infrared, and it's much larger. So why is there such a difference between minimally coupled scalars and conformally coupled scalars? I don't see who's talking. Yeah. Right. The dispersion relation for minimally coupled scalars, omega k squared, has a term that can be negative. That's related to the Ricci scalar. So during inflation, that can be negative. Omega k squared can be negative, so there's a growth. And I have a graph that shows that here. So this shows how k cubed chi k squared grows as a function of A. And again, here at very small values of A, you're in the Bunch-Davies vacuum, but it's constant during, if it's conformally coupled, it will remain constant all the way to the end of inflation. But if it's minimally coupled, it will grow as A squared till the end of inflation. And you can see this just by looking at the expanding the Hankel functions for nu equal to 3/2 rather than nu equal to 1/2. So this is for m over he smaller than 1 and k of 10 to the minus 2. And there's a growth in chi squared during the inflationary period for minimally coupled scalars where there's not for conformally coupled scalars. All right, where is it? And you see this looks much different. I showed this maybe in the first or second lecture. This looks much different. The evolution of this as a function of A looks much different than conformally coupled scalars. So the answer is conformally coupled scalars and minimally coupled scalars are very different. And for comparison, this was an example of the spectrum for a conformally coupled scalar for m over he of 0.1. You can compare that to the result for the minimally coupled scalar. Not only is this is blue, but that spectrum is red, but it's a much larger amplitude. So if we want 10 to the minus 5, then this does not look like a good dark matter candidate for a minimally coupled scalar.
So could you comment more on the XI dependence? For example, what happens if large nominal coupling or negative XI?
For negative what, sorry?
Negative non-minimal coupling or large non-minimal coupling. XI
Oh, for large non-minimal
yeah,
coupling?
like 100 or...
Yeah, so I'm only considering the conformal coupling and minimal coupling. In general, we don't know what the value of C is. And there are models of Higgs inflation where C is very large, 10 to the 4, 10 to the 5, or something. I forget, it may even be negative. I forget what people take. So it's possible to modify this. The problem would be is if the mode equation becomes tachyonic in the inflationary phase, then you're going to have a large growth and you're going to end up with a red spectrum.
So this is the case for the large positive non-minimal coupling, right? Negative, maybe you don't have a...
Right, negative, you wouldn't have that problem, yes.
Thank you.
So, have an inflation model.
If I may, so could you also understand the smallness of the production rate? No, the number density of particle produced in case of the conformally coupled scalar theory as due to the a priori existing conformal symmetry in the theory, and which is only broken by the mass of the particle?
Right, and for the conformally coupled scalar, conformal symmetry is only broken by the mass term. For a minimally coupled scalar, it's just broken.
So does that also describe or explain the smallness of the number density there?
Sorry?
Does that also describe or explain the smallness of the number density in case of conformally coupled theory?
Right, so for the conformally coupled scalar, the conformal symmetry is broken only by the mass, so you would expect ma cubed to be proportional to the mass. So as the mass goes to 0, you wouldn't have any production. But for minimally coupled scalars, as the mass goes to 0, you can still have production.
Thank you.
The quartic potential, I believe, is not conformally symmetric, right?
Just 5 to the 4th instead of the quadratic.
Let's see, I take that back. I don't remember what would happen if it's just 5 to the 4th.
So in that case, the system has a conformal invariance, then maybe there's no particle production from the gravitational effect. I don't know.
I don't know, I'd have to think about it and look back in my notes.
But you say only the mass breaks conformal invariance, so it's maybe...
For conformally coupled, I do know that conformal symmetry is broken only by the mass term. And for minimal coupling, it's broken by the mass term, plus the kinetic terms break it also. So there are two problems with minimally coupled scalars.
I have a question. I was talking to some of the authors who wrote about the comparison between Boltzmann and the Schwinger approaches. I mean, these Bogoliubov approaches. And I try to understand the result in the Bogoliubov approach in terms of Boltzmann approach by making quantum fluctuations in the inflaton or inflaton condensate. I don't know if you, but there's arbitrariness in the quantum fluctuations in the inflaton condensate. I don't know if you allow for velocity dispersion in the inflaton condensate.
So you're assuming that it's not all at 0 momentum?
You're right. The momentum of the inflaton is non-zero. And then if you consider inflaton scattering into dark matter pair, you need to take into account non-zero velocity for the inflaton. in general.
Mhm.
So I wonder if you can explain non-zero particle production for small momentum mode below implanton mass scale. I don't know if it's the, I don't know if you have thought about this possibility, because this, as you said, the Boltzmann approach is intuitive and is more from particle physics point of view.
Yeah. So this is due to the 2-to-2 contribution. And generally, it stops here if, as you point out, you assume there's zero momentum, spatial momentum in the condensate. And of course, for this particular case, there's a much larger contribution for smaller k. So I don't know, if you allow momenta in the condensate, then you could extend this to smaller values of k, but it would be interesting to understand the origin of the momenta in the condensate and what that would give you. But again, as Mr. Lee will tell you, all of this, in principle, is calculated by the Bogolubov method. So this is Bogolubov also, but it's very difficult numerically to calculate it over here for large k because the equations are stiff.
Yeah. Okay, I understand. Yeah.
Thank you. Okay, so let me just point out two problems with the minimally coupled scalar as dark matter. The first problem is Na cubed is too large. The second problem is when you integrate the spectrum is constant for small k, so as you integrate, it's a log divergent, and you have to introduce a cutoff. And perhaps a more serious issue has to do with isocurvature perturbations. So if the Wimzillas contribute to the matter density, the fluctuations in the matter density is not due to the usual fluctuations during inflation, or said again, there are two sources of fluctuations. One source of the fluctuations come from perturbations in the inflaton during inflation, and the other will come from fluctuations in the spectator field. So U, in the usual picture of inflation and generation of density perturbations, U are a amplified quantum fluctuation. So the fluctuations in the curvature during inflation produce fluctuations in the temperature and fluctuations in dark matter if dark matter arises from the usual freeze-out calculation. So fluctuations during inflation lead to fluctuations in the radiation, and the fluctuations in the spectator field will lead to fluctuations in the matter, assuming that the spectator field is responsible for the matter density. And these will be uncorrelated, and we can place limits on the amount of fluctuations in the matter density due to some other source, like the spectator field, compared to the radiation field. These are known as isocurvature fluctuations, because the fluctuations in the matter density, if it's due to the spectator field, are uncorrelated with the curvature fluctuations. So this would rule out, just on this consideration alone, would rule out a minimally coupled scalar as being dark matter. So one conclusion is that stable, minimally coupled, I'll write this down, and I should also say this is stable, minimally coupled scalars without standard model interactions, or ruled out. So it would tell us something about possible, what sort of particles are possible. Okay, let's take a break now and be back at what time? Is NA cubed is too large. The second problem is it is when you integrate the spectrum is constant for small k, so as you integrate, it's a log divergent, and you have to introduce a cutoff. And perhaps a more serious issue has to do with isocurvature perturbations. So if the Wimsillas contribute to the matter density, the fluctuations in the matter density is not due to the usual fluctuations during inflation, or said again, there are two sources of fluctuations. One source of the fluctuations come from perturbations in the inflaton during inflation, and the other will come from fluctuations in the spectator field. So you, in the usual picture of inflation and generation of density perturbations, you are a amplified quantum fluctuation. So the fluctuations in the curvature during inflation produce fluctuations in the temperature and fluctuations in dark matter if dark matter arises from the usual freeze-out calculation. So fluctuations during inflation lead to fluctuations in the radiation, and the fluctuations in the spectator field will lead to fluctuations in the matter, assuming that the spectator field is responsible for the matter density. And these will be uncorrelated, and we can place limits on the amount of fluctuations in the matter density due to some other source, like the spectator field, compared to the radiation field. These are known as isocurvature fluctuations because the fluctuations in the matter density, if it's due to the spectator field, are uncorrelated with the curvature fluctuations. So this would rule out, just on this consideration alone, would rule out a minimally coupled scalar as being dark matter. So one conclusion is that stable, minimally coupled, I'll write this down, and I should also say this is stable, minimally coupled scalars without standard model interactions or ruled out. So it would tell us something about possible, what sort of particles are possible. Okay, let's take a break now and be back at what time? Sorry? Okay, 10:45.
I understood your point. I mean, misalignment is case dependent. I mean, the IATL actually can be understood as a misalignment in some sense,
Mhm.
inflation, but it's already your context.
Yeah, I think so. I think so. Let me think more about your question because I haven't really thought about that.
But for the absent cases,
Sorry. Okay, so yesterday I discussed the calculation of chi k squared as a function of a, starting with the results that we have during the quasi-de Sitter phase, and then depending upon the value of k, whether it's relativistic or non-relativistic, and whether the expansion rate is larger than the mass or smaller than the mass, we could find solutions to the wave equation in this various region and calculate how chi changes with A. And yesterday I made the implicit assumption that the universe is matter dominated during all this time. I did not take into account the possibility that the universe reheats before it reaches this state where chi goes as a to the minus 1. Now, I want to just illustrate what the difference would be if that assumption is relaxed. So, again, you can see the difference here between the conformally coupled scalar and the minimally coupled scalar. Different regions where it goes is a to the 0. But for the minimally coupled scalar, it will be different. It will go as a squared in this region, a to the 0 in this region, and a to the minus 1 in that region. This is detailed in the notes. So if you do the calculation that I described before, say for small k, starting with the value of chi squared from de Sitter, growing during this phase, and then eventually going as a to the minus 1, you would calculate the flat spectrum. This is, again, assuming that it's all matter dominated. So the matter domination would be this for A over AE, larger than 1 and smaller than the value of A when reheating occurs. So this is the evolution during the matter-dominated phase. During a radiation-dominated phase, the evolution is different. The reason the evolution is different I'm always looking for chalk. Somehow I think I should have the chalk around my neck and just being able to pick it up. So let me just use this board over here. So for radiation, the Ricci scalar is 0. So it doesn't matter whether it's minimally coupled or conformally coupled. For a matter-dominated phase, A over AE at late time goes as eta squared. For radiation, it's linear in eta. So when we look at the mode equation, when and this will be when a squared A will bring in a different value of eta depending upon whether it's radiation or matter dominated. So the behavior, the scaling of chi k squared with A will be different. So it's different if the universe is radiation dominated and matter dominated. Now, again, it's detailed in the notes, I hope. Yeah, I'm pretty sure it is. It will make a difference in Na cubed in n sub k. It will make a difference depending upon whether you have early reheating or late reheating. So late reheating will be when the value of A reheat is here. Oh, let me go back one more. Will be here. So if it reheats, once it reaches the non-relativistic phase with H smaller than M, then reheating will not have an effect. The evolution will be constant. So that would be late reheating. Then you could have immediate reheating. Let's imagine you go immediately from inflation to a radiation-dominated phase. Then your result for n sub k will be different. It will be smaller. So for immediate reheating, there's a difference here for this value of the mass of about 10 to the 3. However, it does not change the fact that it will be infrared constant. So it does not turn the red spectrum into a blue spectrum. And you can go through in solutions like this, even in the radiation-dominated era, the solution to the wave equation is always some sort of Bessel function. You know, it's a parabolic cylinder function or something like that. And doing all these special functions is pretty boring to me, but it's something that's straightforward. All right, who's tired of scalars? I am. Let's do something besides a scalar. What do you want to do next? What's the next simplest thing we might do? Well, I'll tell you what I'm going to do next is going to be a Dirac fermion. Scalars are described by a 0-0 representation of the Poincare group. We heard from the lectures, I believe, on Monday that Dirac fermions are the 1/2 0 plus 0 1/2 representation of the Poincare group. This is what I will cover now. And this has spin 1/2. This is spin 0, spin 1. Vectors are described by the 1/2, 1/2, transform as the 1/2, 1/2 representation of the Poincare group. And you can also have vectors that transform as the 1, 0 plus 0, 1 representation of the Lorentz group. These are antisymmetric two-form tensors. This also has spin 1. And finally, I will, not finally, then we can have Rarita-Swinger fermions that transform as the 1, 1/2 plus 1/2, 1 representation of the Poincare group. This has spin 3/2. And we can have tensor fields which transform as the 1, 1 representation, and this has spin 2. And these are legitimate quantum field theories that can be produced from these types of particles. So scalars are familiar to people. And I can remember when there were exactly 0 fundamental scalars that had been discovered. But since 2013, we've discovered exactly 1 fundamental scalar field, and that's the Higgs field. Fermions, Dirac fermions, people are familiar with. Spin 1 that people are familiar with would be electrodynamics. But I will consider massive spin 1 a Proca field because the massless spin 1 field will be conformally coupled. So we will not have gravitational production of photons. This is not part of the low energy standard model, but it exists. It's a fundamental prediction of superstring theory. And it's known as the Kolb-Ramond field. So these exist in superstring theory, and whether superstrings have anything to do with reality is yet to be proven, but there's a motivation for considering it. Rarita-Swinger spin 3/2 fields. There are no fundamental spin 3/2 fields in the standard model, but they exist in supergravity models in the guise of the gravitino. And finally, of course, there is a tensor field, a spin 2 field that's known as the graviton. But I will consider a massive spin 2 field that is not part of the low energy standard model. Now, I've spent a lot of time on this, but once we understand all the machinery and dynamics for scalar fields, it will make it easier, I think, to understand gravitational production of those fields. So today I will do this, and then tomorrow in the morning I will do this. So this is, today's Thursday? Not in Chicago, but here it's Thursday, right? So on Friday I will do this. I will not do this. I will do this on Friday morning, Friday first lecture, and do this in the second lecture on Friday. Okay, spin 1/2 in Minkowski space. So let's start off with spin 1/2 in Minkowski space. And then we're going to promote it to curved space-time, and then look at the specialized Friedman-Robertson-Walker space-time. So we've heard in the lectures before what the field equation is. And we can imagine this coming from an action in Minkowski space. And gamma mu, of course, are the gamma matrices. And the difference between scalars is that the field will anti-commute rather than commute. So again, as we did before for vectors, we can expand the operator in terms of creation operators and annihilation operators. In mode functions, the S will be different spins. So the mode functions U and V and the ladder functions A will anti-commute. A and B will anti-commute. And since psi is not real, the operator is not Hermitian, so there are different operators A and B. And with a choice of the mode functions, the vacuum is defined Okay, so this is sort of straightforward Minkowski quantum field theory for fermions. And the spinners I can choose the spinners U and V. terms of UA and UB. There's probably an S there. And an outer direct product with some helicity spinner. So that would be U. And I guess there's a phase here. And in Minkowski space, there's an equation of motion for U and V that follows from the equation of motion for the fermion. And in case you're interested, I'm going to work in the Dirac representation for the gamma matrices. An old-fashioned representation. And I'll just write this as some matrix A times UA and UB. And here the eigenvalues of the matrix A is lambda plus and minus. Okay, what else do I want to do? I can diagonalize the matrix A. By a rotation matrix. Some rotation matrix such that U, A, U transpose is equal to the diagonal Now, A is going to be time independent in this case. And in the new basis where it's diagonal, we can call it U plus and U minus. It's this rotation of UA and UB. This is sort of straightforward and familiar, but it's going to be different when we do curved space. And in this new basis, the Dirac equation U plus and U minus. So up to a normalization, we can define U plus or minus as the positive and negative frequency modes. Okay, differentiating again with respect to time. We recover a wave equation. So, you know, the usual thing that's said is the Dirac equation is the square root of the wave equation. That might have greatly annoyed Dirac, that statement, but it looks like it to me. All right, so we have chosen a basis, U and V. We can choose another orthonormal basis. Let's call it U tilde and V tilde. And we can relate this to the basis we've chosen. I guess U's a bad. This is not the spinner. We can relate it to the spinners, the old spinners U and V via Bogolubov transformation. Okay, I'm going to leave Minkowski space in about 2 minutes, but I'll just make one more statement. We can calculate the stress tensor by the Hilbert stress tensor and take the trace of it, and the trace of the stress tensor is M times psi bar psi. So the trace of the stress tensor depends upon the mass. So the massless fermion is conformally coupled So we expect that gravitational particle production will be proportional to M, and this gives us a hint that gravitational particle production of the fermion field will be similar to gravitational production of a conformally coupled scalar. And the reason, you know, why worry about conformally coupled scalars? C equal to 1/6 seems like I pulled that out of my nose, or some other, I pulled it out of my nose. Why 1/6? What's so special about 1/6? Because it leads to a conformally coupled theory, and many other higher representation groups, higher spin groups, will have components that are conformally coupled. All right, so we're going to do just like we did for scalars. We're going to promote this to curved space. And to promote it to curved space, we're going to use the tetrad formalism. And I can go forever down the rabbit hole of the tetrad formalism, but I found a nice review of using the tetrad formalism for fermions that I can refer you to. It is a paper, covariant derivatives of fermions and all that. And it is by Mr. Shapiro. forgotten his first name. It's in universe, this universe, not the multiverse, this is universe. And it's 1611.02263. So we want to promote the action in Minkowski space to an action in curved space. And for spinors, we must use the tetrad formalism. So the Dirac equation in Minkowski space will go to, I'll define this in a moment. So the gamma matrix with an underscore is defined in terms of the Minkowski gamma matrix with the frame field. And the covariant derivative, the derivative goes to a covariant derivative, is the normal derivative plus, I think it's a factor of 1/4 times the spin connection that I defined in the first lecture, I believe. And gamma AB is the flat space form of, I guess there's a 1/4 Now, how to get this? I refer to this. But I've already discussed what you have to do. The metric eta mu nu goes to g mu nu, and the covariant derivatives go to covariant derivatives, and the gamma matrices. The vectors here are expressed in terms of the flat space vector and the frame field. So in the paper that I've given you, I calculate, now I want to have it expressed just in FRW. And you can calculate this in FRW and what the frame fields are in FRW. And I'll just quote the result. So the Dirac equation in FRW is this. Well, just as with scalars, the kinetic term is not canonical. So we're going to define a new spinner and go to conformal time. So let's call this capital psi. We're going to define a new spinner. Just as we define a new spinner in defined a new scalar, and we're going to express it in conformal time. So the Dirac equation in FRW in terms of this new spinner in conformal time is something that looks really cool. Looks pretty much simpler. So the difference is there's a new spinner and the scale factor enters. So in Minkowski space, we can set the scale factor equal to 1 and a constant, and you just recover the Dirac equation that you expect from Minkowski space. Now we're going to follow the same procedure as we did for scalars. Just a second. Question, yes? You say there's not an I? Oh. So I'm working with the approximation that chi is equal to psi. Thank you. I was pretty sure there was an I there. Yes. In the equation up here? This term.
Third term.
Third term.
Where you
1,
have
2,
the Hubble
3.
constants and the psi. Yeah. Do you want to comment on that? Why we are getting that kind of interaction?
Yeah, okay. So I can sort of tell you that. So the frame fields for FRW, the non-zero ones, and this term here, AB, gamma AB. This, the spin connection in FRW is in general, it's a complicated thing, but in FRW, this goes to 1/2 gamma 0, 1/2 gamma 0, gamma beta, delta beta I, A dot. So this term in the covariant derivative is going to bring in an A dot,
I see.
which eventually gets factored into H.
So it's kind of some interaction term in the Minkowski space. It will look like some kind of interaction term with.
It's the interaction of the spinor field with gravity. So are you talking about adding an interaction for in the Minkowski?
Yeah, because there is no coupling. The coefficients are
right.
just
This
numeric.
is a free scalar, what is it? It's a spinor field, a free fermion.
Yeah, so if I compare with the normal, let's say electrodynamics kind of theory, you get a coupling constant and that describes the interaction. So this can be interpreted similarly, but it doesn't have any.
Right.
So this is why I was wondering.
Yeah. So just as I considered a free scalar field, I'm considering a free of other interactions other than gravity, a free fermion field.
I got it. Thanks you. Yeah.
Thank you. All right. So now you can just follow your nose. I guess this is maybe an American expression. I don't know if it's a Korean expression. Follow your nose, just do the straightforward thing. Quantize. Express it in terms of mode functions. Have creation and annihilation operators. And define spinors, U and V. Okay, so this just follows the type of procedure that we did for scalar field theory, and we're doing it now for fermions. And the U and V will be in terms of UA and UB. So we're going to follow the same type of procedure, but a nice thing happens, sort of a curious thing happens. The scale factor enters. So the Dirac equation in terms of the spinors UA and UB looks like the one for Minkowski space, except the scale factor enters. And of course, if the scale factor in Minkowski space, the scale factor is 1, and you recover the usual Minkowski space result. And again, the eigenvalues, you can diagonalize this. And the eigenvalues of this matrix is the same as Minkowski space, except now it's A squared M squared. Now we want to diagonalize the field equation. To have this. And the thing that will be different now is that the matrix, the transformation that's going to diagonalize the field equation will depend upon the scale factor. So the matrix that diagonalizes the field equation will be time dependent. So we're still going to have this equation, but now this is going to be a little bit more complicated because A is time dependent. So now let me follow that through. What am I doing? Let me write this and then it'll be a little bit clearer. So I've just multiplied by U and inserted the identity a couple of places. So the right-hand side so this is 1. U times UA and UB is going to be defined as U plus and U minus. This diagonalizes A. And over here on the left-hand side, I have this term. And U times UA and UB is U plus. So the left-hand side is A times U times d eta. And this is what we would have in the Minkowski case, except in Minkowski, the transformation to diagonalize A was time independent. Now it's going to be time dependent. All right, again, I can write U as a rotation. And cosine of phi and sine phi. And the difference between Minkowski space is omega k is now time dependent. And going through the algebra, we end up with the Dirac equation in Minkowski space for U plus and U minus. And C sub k is going to involve the derivative of U transpose times U times the derivative of U transpose. And I should have written this in my notes. And I did. HM, right. This is A squared. So C sub k plays the role of the adiabaticity parameter that we had for the scalar fields. Again, C sub k goes to 0 as A squared goes to 0. So, excuse me, at initial time, it's adiabatic. So at initial time, the wave equation is just, U plus and U minus are the solutions. At late times, it goes to 0, 2, and it becomes adiabatic at late time because H will go to 0. And this is K over M times the adiabaticity parameter that we had for scalars. So the Dirac fermion resembles a conformally coupled scalar. Resembles is not exactly a conformally coupled scalar, but it resembles the conformally coupled scalar. And if you calculate, go through the calculation, integrating the mode equation, starting with the Bunch-Davies vacuum, calculating things on to late time, this is the Majorana fermion result. For Dirac fermion, you would just multiply this by 2, compared to the scalar, to the conformally coupled scalar. And you see it is very similar. So the Dirac gravitational production of a Dirac fermion is very well approximated by gravitational production of a conformally coupled scalar. Isn't that a miracle? Well, maybe it's not a miracle. And again, it just traces back to the Dirac fermion is conformally coupled. So, I spent a lot of time developing the formalism and insight with scalars because it just translates here into fermions. Yes.
So it seems like the general slopes are quite similar.
The
But
what, sorry?
if I compare the two cases, the Majorana fermion and the scalar, the conformally coupled scalar cases, generally the slope is very, very similar. But then I noticed that there seems to be quite probably simply expressible like multiplicative factors. Like they're only different biofactors, like
Yes.
multiplicative. So is there any like a simple explanation for why that?
Well, the idiopaticity parameter is not exactly equal. So I said it resembles a conformally coupled scalar, but it's not exactly a conformally coupled scalar.
So that difference reveals the history of the evolution of diversity parameters in the universe before we're looking at the number density.
Yes,
I
yeah.
see.
And there's also, even for a Majorana fermion, there's 2 degrees of freedom. So a factor of 2 here is just accounting for that. So it really is very similar.
Thank you.
Yes, a question up here.
I'm just a little confused. So let's say you produce those Majorana fermions. So do they have interaction with other standard model particle? If that, then let's say the decay of the inflaton and the production is happening at the same epoch. Can you comment on that?
You can make it arbitrarily complicated by adding other couplings. So here I've just assumed that I'm introducing a spectator field of a massive fermion that's not coupled to any standard model particles.
I see. This is a generic question. So far we have followed kind of a tree-level production through gravity. So now these interactions are not renormalizable, right? Like
Or
the fermion, graviton, the last one.
Mm-hmm.
So are there works like if you have gravitational production through loops, and are they divergent?
Well, again, you have to do a renormalization. If you go through the details, just as we did with scalars, you're going to see it's infinite, and there's a normal ordering prescription that you're going to follow. This is a calculation completely on shell, so there's no loops involved. And there's no complication or no beauty of coupling the fermion to other fields.
Yeah, this question was related to the coupling constant question, because as you consider loops higher order, then the value of the couplings matters. So this is why.
Yeah, no, that's not considered here.
Another thing is
that's a homework problem for you.
Another question is that this is, so if I consider Majorana fermion, their charge conjugate, so they will not couple to photons. But this is the question related to one of my questions is that if I consider Dirac fermion, I would expect, let's say if they couple to photons, then they would affect the radiation era or
Well,
not.
they could be coupled to a dark photon.
I see, yeah.
So it needn't be coupled to the photon that we know and love. The photons are coming from the light here.
But if they do, then that would affect the radiation dominant era. Thanks.
So there's another homework problem for you. So, one of the interesting things about this, there are a lot of avenues you can take in gravitational particle production that has not been completely explored.
So naively, we can probably add a non-minimal coupling like R psi by psi, which is dimension 5. Then Could you briefly mention what would you change?
Right, so let me make a comment about that. So for the scalar, we entertain the possibility of a coupling of phi squared times r. And this is a dimension 4 operator. Now, you can also, for a fermion, have a non-minimal coupling, let's call it psi times r times psi bar psi. This is dimension 3. This is dimension 2. So this is a dimension 5 operator. So there must be some mass term or some other mass dimension to have a dimension 4 operator in the Lagrangian. And it's often assumed that it's the Planck mass. So you can add this in the same way that you could add another term something like that. So you can add, and also instead of r squared, it might be r mu nu, etc. So there are a lot of non-minimal operators that you can add in the, so I'll say the magic word effective field theory and say that in the effective field theory, I can ignore this because it's a higher dimension operator, and I can ignore that because it's a higher dimension operator. So I'll say I will ignore all irrelevant operators and say they are irrelevant for a reason because I ignore them. But again, there are a lot of avenues to be explored here. All right, thank you. Tomorrow, I'm going to march on to spin 1 in the morning and do spin 1 and spin 3 halves in the morning. And the second lecture will be a PowerPoint presentation of spin 2, because spin 2 will be more fun. Okay.